Welcome to the course on numerical linear algebra and application. Today we are going to learn 12th module, 58th lecture of this course. As we did some examples in the previous lecture, in this lecture also we would like to attempt few examples pertaining to the differential equations where ultimately the solutions we need to find out, and in the course of action we would able to solve the matrices. Well, 2 point boundary value problems. The boundary value problems, you have the differential equations with dependent and independent variables. If the value of the independent variable, say x in this case, is prescribed at two different points, then we call it as the 2-point boundary value problem. And there is a fundamental mathematical problem. We develop a numerical technique for approximating the solution of 2-point boundary value problems. So what we are going to do is, we will develop a numerical technique. These numerical techniques, when you are trying to solve it, in the course of time we will have matrices. So that is the reason that how the matrices would have an applications in differential equations. If you look at this y double prime, that is f of x, y, y prime, where x lies between a comma b. Alpha 1 y1 a, alpha 1 y of a plus alpha 2 y prime of a is equal to alpha 3. Beta 1 y of b plus beta 2 y prime of b is equal to beta 3. Where f is an arbitrary function of its three arguments, and this is of the form that is f of x, y, y prime. That will be equivalent to p of x times of y prime plus q of x times of y plus r of x. For some functions p, q, r, the boundary value problem is called linear problem. So when the boundary values are linear, when the boundary conditions are linear or the differential equation is linear, then obviously it becomes boundary value problem is linear. Otherwise, we call it as non-linear problem. So non-linearity may arise not only because of differential equation, but also maybe because of the boundary conditions. The boundary conditions given in above, in which the value is specified for a linear combination of the unknown function and its derivative, we call it as a Robin type boundary condition, that is mixed boundary conditions. The special case in which the value of the unknown function is specified, that is y of alpha, y of a is equal to alpha, y of b is equal to beta, which we call it as Dirichlet boundary condition. While the special case is in which the value of the first derivative is specified, that is y prime of a is equal to alpha, y prime of b is equal to beta. So in this case we call it as a Neumann boundary conditions. More general boundary conditions such as periodic conditions can be specified, but we will not be considering over here. Oscillatory boundary conditions, periodic boundary conditions, abrupt variations, and so on and so forth. So if you look at the very particular example of the matrices, that is steady state temperature distribution in a fin. So these kind of problems you do come across quite often in the heat transfer. The term extended surface is used to reference a solid in the experiences energy transfer by conduction within its boundaries and convection between its boundaries and the surroundings. The most common application of an extended surface is to enhance the heat transfer rate between a solid and an adjoining fluid such as air or water. Extended surfaces used in this manner are called fins. A fin that has a circular cross section is called a pin. So it's very important. Extended surface used in this fashion, which we call it as a fins. A fin that has circular cross section, which we call it as a fin. Suppose we have a fin of length L, that is length L, varying radius R of x. Attached to a surface as shown in below figure, would like to determine both the temperature distribution along the length of the fin Tx and the total fin heat transfer rate Qf. So this is the one which we get it. So you see, this is the direct delta x, this distance is delta x, that is elemental change, and this is the qx, this is the q convection, and that's how you do get as qx plus dqx upon dx times of delta x. A fin with uniform, that is, or non-uniform cross section, that is energy balance on an arbitrary surface or slice of fin that experiences convective heat loss from its lateral surface. Performing an energy balance on the arbitrary slice of a fin shown in the figure, so you will have this figure, that is qx is equal to q of x plus dqx upon dx times of delta x plus q conversion, where qx is the rate of heat transfer along the length of the fin due to conduction and q convection is the rate of heat transfer from the lateral surface of the fin due to convection. So according to the Fourier's law, you will have this equation, that is q of x is equal to minus of Ka times of dt by dx, where K is the thermal conductivity of the fin and A is the area through which the heat flows. K is the thermal conductivity of the fin and A is the area through which heat flows. The minus sign indicates that heat flows from regions of high temperature to regions of low temperature. The convection heat transfer rate is given by this expression, that is Q of convection is nothing but H times of As T minus T infinity. Here H is the convection heat transfer coefficient, As is the area of the surface from which the convection takes place, and T infinity is the temperature of the adjoining fluid. Substituting 2 and 3, so you do get as A is equal to pi times of R of x whole square and A of s is equal to 2 pi R x times of delta x. So you get the equation like this: d by dx of Rx of 2 dt by dx minus 2h by k Rx times of t minus t infinity is equal to 0. At x is equal to 0, where the fin meets the solid, the temperature of the fin equals that of the solid T naught. Then we have the boundary condition, that is T of 0 is equal to T of naught. So you do have a equation like this. So that is so you'll have, that is J of x plus delta x. So the boundary conditions would be like this, that is minus k times of t prime of L will be equivalent to h times of t of L minus t of infinity. The boundary value problem given in 4 and 5 and 6 determines T of x. Once Tx is known, the total fin heat transfer rate is given by this expression, that is Qf is equal to minus of K phi R0 square T prime of 0. Spatial distribution of an insect population. Using the information from figure 2, the conservation loss becomes, that is this expression. So you will have J of x minus J of x plus delta x, okay, multiplied with A plus f of n comma x, A times of delta x is equal to 0. So during this equation, that is A times of delta x. So delta x tends to 0, then you will have minus of dj upon d of x plus f of n comma x is equal to 0. To proceed further, we relate the flux to the population density by assuming Fick's law, which states that J is proportional to the gradient of n. Then you will have this expression, that is J is equal to minus of d dn upon dx. The coefficient of diffusion d measures the efficiency with which the insects disperse, and the minus sign indicates that migration takes place from regions of high density to regions of low density. For the source term, we will use the logistic growth like this. This is the expression you will have. So f of n comma x is equal to r times of n of 1 minus n over k, where r is the reproductive rate of the insects and k is the environmental carrying capacity. Substituting 9 and 10 into equation 8 and assuming that d is constant, so you will end up with this equation, that is d times of d of n upon dx of 2 plus r of n times of 1 minus n over k will be equivalent to 0. So with this expression, you will have n of 0 is equal to 0 and dn of 5 dx of L is equal to 0. If we now introduce the non-dimensional variables, n is equal to capital N by k and x is equal to x times of square root of r upon d, we arrive at the following boundary value problem. So that is n double prime plus n times of 1 minus n is equal to 0 and n of 0 is equal to 0 and n prime of L is equal to 0. So if you apply the finite difference method, we will begin our study of the finite difference methods by investigating the linear problem. So that is this problem, y double prime is equal to px times of y prime plus qx times of y plus r of x, where x belongs to, that is a comma b. So you will have this expression y of a is equal to alpha and y of b is equal to beta. The objective of finite difference method is to approximate the value of the exact solution to the boundary value problem yx at a discrete set of points x0, x1, x2, xn belongs to AB. Throughout our discussion, we will let us yi denote the value of the exact solution at x is equal to xi, and we will denote our finite difference approximation to yi as yi by wi. This finite difference approximation is obtained by replacing each derivative which appears in the boundary value problem. So you will have discrete algebraic equations w0, w1, w2, w3, w of n. The computational grid is, to begin the approximation process, we must first introduce a partition or a computational grid over the interval AB. Let n be a positive integer that denotes the number of subintervals in the partition and denote the partition itself. So we will write this partition as, that is a is equal to x0 less than x1 less than x2 less than xn is equal to b. The points x0 to xn are called boundary grid points, while the points x1, x2, xn are called interior grid points. So that is, we will assume that xi is equal to a plus ih, where h is equal to, this is h is equal to b minus a upon n. The parameter h, known as the step size or the mesh size, is the key parameter governing the accuracy of the finite difference approximations. So the finite difference approximation is, once the computational grid has been established, we evaluate the difference equation, that is equation 13, at each interior grid point. So you will have y double prime is equal to px times of y prime plus qx times of y plus rx, that is at x is equal to xi. And then replace all of the derivatives by second order central difference approximations. So that is y of I plus 1 minus 2 yi plus yi minus 1 divided by h square plus order of h square. To simplify the notation, we have used pi, qi and ri to denote the coefficient functions, that is px, qx and rx. So we drop the truncation error term exact solution by approximating these values. So w of I plus 1 minus 2 wi plus w of I minus 1 divided by h square will be equivalent to pi times of wi plus 1 minus wi minus 1 divided by 2h. To completely determine the unknowns w0, w1, w2, wn, two more equations are needed. These are all will come from the boundary conditions. So we will have y of x0 is equal to alpha, y of xn is equal to beta. Have been specified, therefore we will set up, that is w0 is equal to alpha, wn is equal to beta. Combining these equations, so we get what you call this, since the truncation error is order of h square. So the resulting numerical method will be second order. So this point will be discussed during the demonstrative process. Look at this equation. So wi plus 1 minus 2 wi plus wi minus 1 h square. So this is basically d2w upon dx of 2. And this is for the central differences, that is dw upon dx, and wi plus 1 minus wi minus 1 divided by 2h. So when you get into the equations of numerical methods are linear, in the unknowns we will express the systems in the form with w0 and wn, that is w0, wn are from the Dirichlet boundary conditions. So there are n minus 1 unknowns to be determined. So to construct the coefficient matrix and the right hand side vector for the system, so then you will have what you call, you will end up with an equation of this form. So this is the one which you get it. Hence the coefficient matrix will be tridiagonal. The first row corresponding to I is equal to 1 and the last row corresponding to I is equal to n minus 1. So you get this equation. So they look at this, minus 1 plus minus of h by 2 times of p1. That is the first term associated with w0. Second term is 2 plus h square times of q1 associated with q1. Third term is minus 1 plus h by 2 times of p1 associated with w2 is equal to minus h square r1. This is the equation which you get into that. Substituting w0 is equal to alpha and transposing the first term in the right side, so you will have expression like this. As the first equation of the system working in a linear manner, so you get the equation of this forms. So minus 1 plus minus of h by 2 times of pn minus 1 multiplied with the w0 plus 2 plus h square qn minus 1 times of wn minus 1, which will equal to minus of h square rn minus 1 plus 1 minus h by 2 pn minus 1 times of beta. So the system of equations for w1, w2, w3, etc. So we write into this first. Now you look at here, this is the main diagonal, this is the subdiagonal, this is the another subdiagonal. So we will have zeros. So ultimately you will end up with what you call a tridiagonal matrix. Tridiagonal matrix. So with di is equal to 2 plus h square ui and ui is equal to minus 1 plus h by 2 pi, li is minus 1 minus h by 2 pi. So the vectors A and B are in this form, that is w is equal to w1, w2, w of n minus 1. And B is equal to this matrix, you do get this matrix. Note that the boundary conditions have been incorporated into the first and last entries of the vector B. Solubility of the discrete equations. Does this system of algebraic equations have a unique solution? Let's suppose that P is continuous and that Qx greater than or equal to 0 on AB. By the extreme value theorem, the continuity of P over the closed interval AB guarantees the existence of a positive constant L such that is modulus of P of x is less than or equal to L on the interval a comma b. If the step size h is chosen to be smaller than 2 by L, then for each I, that is minus 1 less than HPI divided by 2 less than 1. So you get into expression this form. So therefore, when you write this equation, so you can write it as minus 1 minus h by 2 pi, that is absolute value of this is equal to, so you get as 1 plus h by 2 times of pi, and second equation you get as 1 minus h by 2 times of pi. So that the two rows of this matrix will become like this. So that is absolute value of minus 1 minus h by 2 pi plus minus 1 plus h by 2 pi, so which you get it as, that is 2 plus h square by h square times of qi. That is rows 2 through n minus 2, the sum of the absolute values of the off diagonal entries is less than or equal to the absolute values of the diagonal matrix. So the first and last rows of satisfies an even stronger condition. The sum of the absolute values of off diagonal entries is less than the absolute values of the diagonal element. Hence A is diagonally dominant with its first and last rows being strictly diagonally dominant. These conditions are sufficient to guarantee a unique solution to our finite difference equations, provided that step size is less than or equal to h is less than or equal to 2 by L. So in this lecture, what we have seen is how these finite difference method for the differential equations would be transformed into difference equations, which leads to the finite difference method, and ultimately we transform that equation into the triadiagonal matrix. So therefore, all that what it remains is how to find out the triadiagonal matrices. So therefore, this is one of the applications of the matrices we use in differential equations via the numerical methods called finite difference method. So we'll see some more examples in the next two lectures. Thank you very much for hearing my lecture for today. Thank you once again.